ado, let me introduce our next speaker, and I appreciate him for waiting. Sorry about that. It's Dr. Bruce Banerdt is the lead scientist for GEMS, which stands for the Geophysical Monitoring Station, to look at the core and the crust of Mars, and I'm really excited to hear all about that. Please welcome Dr. Banerdt.
So good morning, everybody. So I'm here to talk about what is perhaps going to be the next new mission in the Mars program called GEMS. Right now it's called GEMS. We were told when we got the word from NASA that we were going to have to change the name because there's already some other silly mission somewhere that has a name GEMS. So if anybody has really good ideas, send it to me by email and I'll put it on the list. And if I choose your name, you'll get some little tchotchke that has a name on it if we actually decide. Okay, so before we get into that, though, I wanted to talk a little bit. I mean, the theme of this convention is Mars, the next frontier, right? But some of us are actually lucky enough to be actually working on that frontier every day. I also happen to be the project scientist for the Mars Exploration Rover, and so that's my day job. Okay. And this is an image from the downlink on Friday. We've been going the last 2 years from Santa Maria Crater headed towards Endeavour Crater. You may have been following it, and we just this week finally got to the rim of Endeavour Crater, and we're looking over the rim. That far rim over there is about 25 kilometers away, and you can see the mountains ring the crater going off in the distance there to the right. And we're finally looking over the edge there, and we'll be studying that place. And then this is the latest downlink. It's not even, we don't even have a scene-corrected mosaic for this year. I just put this together in Photoshop last night. And so you can really see the enormous topography that Opportunity's finally gotten to. And this is really exciting for us because Opportunity has not seen any topography more than maybe 2 or 3 meters for its entire journey. So this is really great stuff. So we're actually on the frontier of Mars right now, and we're waiting for the rest of NASA to catch up with us. Okay, so moving on. What is GEMS? Okay, GEMS is a Mars geophysical lander mission managed by JPL, and with the hardware based on the Lockheed Martin Phoenix spacecraft, which you probably guessed from the opening slide. And we were recently selected by NASA in the Discovery program, which is a competitive program that NASA puts out every few years for small planetary missions, less than $500 million. That's small. Okay, so we were selected along with 2 other missions to do what's called a Phase A study, which is about 9 months where we get a more definition on the mission and get the engineering stuff just a little bit more refined, and then there'll be a down selection after 1 year. So we may or may not go forward, but we've been selected for at least for the first step of this process. Okay, so our goal is to map the deep interior of Mars, something that has been sort of missed by the Mars program for the last 45 years, and I'll tell you a little bit about why that's important, why we think it's important, and how we're going to do it. Okay, so the GEMS objectives are key focus. Okay, we're going to put a single geophysical lander on Mars. We're going to measure seismic activity, heat flow, and planetary rotation. Okay, so we don't have a big Christmas tree of instruments on our payload. It's very, very few instruments, but they will give us a really rich data set. With those instruments, we ought to be able to determine things like the size and state of the core, the thickness of the crust, the structure of the mantle, and the thermal state of the planet, and be able to give us a measure of the seismic activity and the rate of meteorite impacts on Mars. Okay, so first of all, this is kind of cool stuff, but is it really that scientifically interesting? This is just kind of like underground geography, right? It's like you're mapping out things, and what does it actually tell us about Mars? It actually tells us a great deal, not only about Mars, but about the whole solar system. Okay, so these are the terrestrial planets. There's Mars on the far right, and Earth sort of right next to it, Venus, Mercury. And if you look inside those planets, which we have some ways of doing, and we can guess at some of the other ones, you see they all have the same kind of structure. They have a core, a metallic core at the center. They have a rocky mantle that's conducting a lot of heat out of the planet, and we've got a sort of a frozen crust on the outside that we walk around on and call home. But how do they get that way? That's one of the big questions in planetary science. So we start out with accretion, things connecting together. That's not my problem. I don't care about that. Well, I do care about it, but I don't know about it. So I start out with accretion, but how does the planet evolve from there? Okay, so you start out with sort of these things knocking together and accreting into bigger and bigger blobs. They get to some point, they start to heat up, both due to the energy from the impacts falling in and from the decay of radioisotopes in the rocks. And then at some point, stuff happens, the heavy material sinks, the lighter material floats, and you end up with a crust, mantle, and core. Okay, so wait a second, so stuff happens? I mean, this is kind of the crucial place. This is like, a miracle occurs. So this is really what we want to figure out. What's the stuff that happened to go from this kind of cold, rocky, homogeneous, accreted body into the fairly complex bodies that we see in the solar system. Okay, so we have some ideas on how this happens. We have some pretty good ideas on how it happens. So we know that core formation, or we're pretty sure that we know that core formation happens as the planet starts to melt. You have droplets of metal that kind of condense out of this melt. They're much heavier than the melt. I mean, rocks have a melted density of around 3 to 3.5 grams per cc, and metals are more up in the order of 5 or 6. So they're quite a bit heavier. So they're going to fall down through this what we call magma ocean, which is the melted outer portions of the planet. And even when they get to the solid part, things are hot enough that there's a solid state flow, and these things can fall through it and form a core at the center. Forming the crust and mantle is a little bit more complicated, but we also kind of know how that goes from studying the moon. You end up with we start off with a planet that's molten. Maybe it's all the way molten, maybe like this is, or maybe it's only molten on the outer parts. And when this molten sea of rock starts to crystallize, it crystallizes in a very complex way. It's not like you have water, you get it, you start cooling it down, and ice crystals form, and that's it. A magma is a very complex chemical mixture, and as it cools down, you have different kinds of things that come out of that melt, that crystallize out of that melt at different temperatures, pressures. You have different rocks and minerals, and that's why a planet has such a wide diversity of rock types. So you have some of these, like pyroxenes and olivines that sink to the bottom. You have other things like northicites that are lighter and they go to the top, and so you end up with a pile of crystals at the bottom of heavier rocks and this floating crust of lighter rocks. And then there's a lot of complexity that goes into there because they change phase, they get denser, sometimes the whole thing flips over and stuff like that. But this is kind of the basic framework of planetary formation. And this is really the details of this process are what we want to get to. So once we form this crust, we form the mantle, we form the core, what happens for the rest of the time is basically the planet is just trying to get rid of all the heat. Gets rid of the heat both from its formation and heat that's generated by these radioisotopes. And everything that goes on a planet from there on is really driven by this heat engine. Okay, it gets the heat out by convection, by conduction. It gets heat out by freezing, specifically freezing. It pushes heat up to the surface through volcanism. Plate tectonics is actually a very efficient way of getting heat out because you have the molten material coming up to the center of the place and they go out and they cool, and then the cold stuff goes down to cool the interior. So there's lots of ways that a planet gets rid of its heat, and all those ways have a very strong imprint on the surface of the planet. The part of the planet that we walk on, the part that we can observe directly. And so these are really key processes in getting planets where they are today. So how can we use this underground geography, the thickness of the crust, the size of the core, whether it's liquid and solid, maybe what the thermal state is, how can we use these sort of very basic parameters to explore planetary history? And what I've done in the next couple of slides is I put in bold color the things that we can actually measure, the things that are very easy to measure. So one thing we can do is look at the crust, and the thickness of the crust right away, just the volume of the material there, tells us a a lot about the very strong constraints on the depth and evolution of that magma ocean, whether it was a planet-wide magma ocean, whether it was just the outer few hundred kilometers, just how big it was, how much of that actually melted, and then crystallized into crust and mantle. And subsequently, that thickness is then affected by things like plate tectonics, whether you had the crust of the planet that actually is involved in the convective processes of the mantle, or whether it just sits there very stationary and things are just trying to push up through it. And so just having that one parameter, the thickness of the crust, tells us a lot about the very earliest history of the planet. The core is another sort of key parameter. Again, we can measure the density of the core, we can measure its temperature, we can measure whether it's solid or liquid, and whether it's maybe even both, like in the case of the Earth, where you have a liquid outer core and solid inner core. All these things are very strong pieces of evidence for processes both early in Mars' history and going up to today. So the composition of the core, which is really not just whether it's how much iron and nickel in it, which is pretty easy to determine, but how many lighter elements, sodium, carbon, things like that, got pulled into the core during that process of those droplets coming into to make the core. That tells us about both the composition, that initial accreted body, and also about the chemical conditions, the oxidation state, and the mixing of that original body. Then of course, size and temperature is one of the major drivers on whether that mantle is convecting, whether it's conducting, how that heat is getting out of the mantle. And so not only is it the lower boundary condition, but it actually can affect how the mantle behaves by determining the depth of the lower boundary, which tells us about something about phase transitions, which can actually block the transport of heat out. And of course, it also has implications for the dynamo, whether it has a magnetic field. And it turns out that a magnetic field is really crucial in the case of Mars in particular for the ability for a planet to harbor life, because the magnetic field shields the atmosphere from solar erosion, and the atmosphere shields the surface from radiation. So really having a magnetic field is thought to be kind of crucial in order to have a planet that's habitable. So the dynamo in the core, which again is related to the thermal history, the thermal state of the core, is really a crucial piece of the history of the planet that we need to know about. And then finally, the mantle. Of course, the behavior of the mantle, like I said, whether it's convecting, whether it produces magma through partial melting, is a very strong driver on the surface processes, and we can get to that through the thermal structure and the compositional or mineralogical stratification in the mantle, whether there's layers in there or whether it's well mixed. Is kind of a basic observation that tells about how this planet got to where it is today. Okay, so far I've been talking just about planets in general, what we want to do for a given planet, but why is Mars in particular important? And it turns out that for the Earth, these kinds of observations don't tell you very much about the early history. And that's because mantle convection on the Earth has been so vigorous, it's mixed the mantle up a lot. There's no signature of the early processes left in the mantle. And the same is true of the crust. You probably know that due to plate tectonics, there's no crust on the Earth. Blocks of crust that are more than maybe a couple of billion years old. And so we're looking at processes that happened in the first few hundred million years of planetary history. They're just not there anymore. I mean, from the Earth, we can find little tiny particles of rock that survive from the earliest part of Earth history. We can't find blocks of crust. We can't find big hunks of mantle that survive. Mars, though, is almost certain to have retained that evidence. We know that because of the analyses of the Mars meteorites that we found in Antarctica. We do isotopic analyses on those, and they show that there are distinct reservoirs, distinct pieces of mantle that have maintained a distinct character through the entire history of Mars. So there are pieces of mantle that have not communicated with each other, so to speak, over the last 4 billion years. Plus, we know that much of the Martian crust, most of the southern islands on Mars, it dates back to the first 500 million years of Mars' history, and we know that from dating it through crater counts and things like that. So we have a lot of confidence that the measurements of the Martian interior can really tell us about the processes of differentiation and early planetary formation that we don't have Mars is kind of in the sweet spot. You know, it's small enough to have not been completely erased. All these evidence has been erased, but on the other hand, it's big enough to where it's undergone these processes. That's not true of the Moon. The Moon is so small that we really don't even get hardly into the upper mantle of the Earth in terms of conditions. And so Mars has all the structure that the Earth has in the upper and even down into the lower mantle and the core. And so we think that it's a good analog for terrestrial planets in general. And again, we can get that signature just from basic measurements. We don't really have to get that fancy in order to tell us something about planets. Okay, so how do you go about exploring the interior of a planet? There's a whole host of geophysical techniques you can use. You use gravity, which is really good for relatively shallow stuff. But if you know the mathematics behind it, it's really ambiguous. You can't ever get a really solid handle on interior stuff. You can use rotational dynamics. It turns out that if you watch the spin of a planet, the spin pole moves around, and the way it moves around, both in terms of precession, which is the slow motion over tens of millions of years, or faster variations, which are called mutations. These are all related to the internal density structure of the planet, and specifically, it's most affected by the size and density of the core, and to the viscous response, which of course is related to whether the interior is melted or partially melted. Electromagnetism, we have the dipole magnetic field of the planet tells us about the core structure. We don't have a dipole field on Mars, at least not one that's large enough to be sensed by orbiters. Crustal magnetic fields tell us lots of things on Mars. We have these wonderful. Unfortunately, we don't understand any of it. And if anybody tells you different, they're blowing steam. Heat flow is a critical boundary condition for determining both the thermal state of the interior and the distribution of radioactive materials in the planet. Turns out that these materials are carried in fairly unique ways on the Earth and the Moon. They're segregated in certain areas, and that tells us something about how, again, that planet, those crusts evolved. And on Mars, that's going to be one of the pieces of the puzzle. And finally, seismology, which I have to devote a couple of slides to because it's really by far the most effective method we have for probing deep into a planet. Probably 90% or more of what we know about the interior of the Earth has come from seismology. I don't know whether people are usually aware of this, but we get almost everything we know about the Earth from seismology, and most of what we know about the Moon's interior and that we've extrapolated to the other planets also comes from the short-lived or the relatively short-lived Apollo seismic experiment. And the reason is because seismic waves, when they pass through a planet, they're affected in many different ways by the material which they pass through. It changes the speed, it changes the direction, the amplitude of the waves, the frequency of the waves, the polarization of the waves, the partitioning between the P and the S waves. You have different kinds of waves, P, S. You have different kinds of surface waves. And so there are an almost unlimited number of techniques you can use to basically process these signals that are going through the Earth and then turn them into information. Since seismic waves are elastic waves, they respond to elastic constants, density, and attenuation properties, and you can relate those to specific rocks that you can measure those properties in the laboratory, and then you can deconvolve all the different effects as it's gone through to derive the planet's structure. And so I like to say a seismic event is like a flash bulb that goes on inside a planet, and all you have to do is have the right camera there to take the image, and that camera is made up of seismometers. Okay, and you don't have to take my word for it because all these high-level science advisory panels dating back to 1978 have had recommendations, strong recommendations for exploring the interior of Mars. And these are both the National Academy panels, NASA advisory panels, ESA advisory panels, the whole works. And so for the last 40 years or so, this has been one of the top goals of the planetary science community. But why haven't we done it yet? Okay, if you're so smart, how come you haven't done it yet? So I'm going to take a little detour and do a brief history of Mars seismology, which is more extensive than you might guess. Okay, so Mars seismology starts off with Viking, 1976. It had a seismometer on it.
The first seismometers we sent to Mars, it was going to do the seismic background, going to get the nature and location of tectonic activity, try to get something about the influx rate of nuke meteorites, and get something about the structure and composition. It was a fairly modest experiment. It was sort of the last instruments on the payload. It almost got pushed off a couple of times, but we had a lot of hopes for it. But unfortunately, none of these goals were accomplished. It was a complete failure as an experiment. One of the seismometers didn't even uncage. They have to hold it for landing because they're very delicate instruments. So the first one failed to uncage. There was a fuse that blew. No data at all. The second site was really far from likely centers of activity. The mounting on the deck, it never got off the deck. It was mounted right to the deck. And you can see those big shock absorbers in the legs. Well, shocks are exactly what we're trying to measure here, so it's not the optimal experiment. So really we didn't get any good data. So these turned out to be the last seismometers from Mars, but we learned a lot of lessons from this, the lessons that we can apply to today's experiments. First of all, the seismometer has to have good coupling to the ground. Okay, so you see in the picture, there's the seismometer, there's the ground. In the ideal case, those two arrows would coincide, but they did not for Viking. So that's one of the big lessons. We found that we can get an increase in the signal-to-noise ratio of at least 1,000 just by taking it off the lander and putting it right next to it. So not shielding it from the wind itself or anything, just getting it off the lander would do it. We need a pretty sensitive instrument. The Viking seismometer was about 3 or 4 orders of magnitude less sensitive than a typical research seismometer on the Earth. Mars is a smaller planet. Seismic events are likely to be fewer and far between, and so you really need all the sensitivity you can get. And you need an adequate data volume. I mean, the seismometer only got a few minutes of data per day down, so it did a lot of compression. It did a lot of off time, and so that makes it more difficult to get the number of seismic events you need to do these analyses. Okay, so the next foray into seismology was by the Soviet Union, which before this thing launched became Russia. It was Mars 92. It turned into Mars 94. Turned into Mars 96. They have the same kinds of problems we do at NASA. And so this was a really ambitious mission to put multiple landers on Mars. It had 2 orbiters. It had 4 different landers that were going to be put down. All those landers carry seismometers, and 2 of them actually had some fairly sophisticated French seismometers. It was launched in 1996 from Baikonur and landed a few hours later in the Pacific Ocean. So none of those experiments were reflown. Well, some of those experiments were actually, the European experiments on that were reflown on Mars Express, but none of the landed experiments had ever been flown. In 1989, there was a Mars Network mission that was being considered by NASA. This was part of the Space Exploration Initiative. Some of you old-timers might remember during the first Bush administration, there was a big program that was going to do a push to Mars, and it was going to start off with a bunch of robotic precursors. This was the first of those precursors. It was going to be 16 different landers all over Mars with nuclear-powered penetrators. They're going to do seismology and meteorology and a bunch of other stuff. The estimated cost was $1.5 billion in pre-1990s dollars. When that number hit the White House, it was canceled pretty thoroughly, along with the rest of the space exploration initiative. But it was sort of reworked first by NASA Ames and then by JPL into a lower cost mission, about half the cost of that mission, called MEASURE, which was the Mars Environmental Survey. This concept evolved for about 6 years, and actually Mars Pathfinder was supposed to be a pathfinder for these network landers, and it went along for a while. And then it was killed in 1996 by ALH 84001 when NASA sort of turned on a dime, became an astrobiology agency, and this is the only confirmed destruction of a planetary mission by a meteorite. So. Meanwhile, ESA was working on these missions as well. They had a mission that competed in the Phase A competition for their second medium mission opportunity, had 4 landers. It was going to be a collaboration with Measure to extend that network from 16 to 20 landers. They couldn't do it all on their M2 budget, so they really had to do it as a collaboration, and it failed selection in '93 because they really never were able to put together a plausible NASA collaboration. They were just going to sort of piggyback on it, and that wasn't very attractive to the Europeans. So they reworked it a couple of years later into InterMarsNet. They actually worked really closely with NASA that time, and they put together a really good collaboration. But they failed selection in '96 when NASA basically pulled the rug out from under them at the selection meeting, and because they'd already selected switched priorities to a biologically driven sample return strategy, and so that one sort of didn't get off the ground either. The French and Germans sort of recycled this idea in '98 with a mission called Netlander, which was supposed to originally was going to piggyback on Mars Express. The ride that Beagle 2 eventually got was originally going to be done by this Netlander package, which unfortunately was a little bit too heavy for Netlander. As soon as the orbiter mass grew, they dropped that and went with the lighter and much more reliable Beagle 2. That's sarcasm. But at the same time, NASA had again, taken this biological goals for Mars and put together the sample return mission in the late '90s. And as part of that, they went into a partnership with the French. The French were actually going to launch it on one of their Ariane 5s and supply the orbiter. And part of that deal, the French required that we carry these Netlanders to Mars. And so it became an integral part of the sample return mission. And of course, since it was an integral part, when NASA canceled its piece in 2000, it kind of started to go downhill. And NASA maintained it for a long time, several years as part of their premier mission, but eventually had to cancel that due to lack of U.S. support for the payload and a change in French government. And so it was finally canceled in 2003. Resurrected one more time for ExoMars. It was part of the original ExoMars mission, one of the original ExoMars missions. There was a geophysical platform package that was integrated into the landing platform that had heat flow, seismometer, X-band precision tracking. But that also was canceled. Actually, that's canceled 3 different times and kept on getting resurrected, but the third time finally stuck, and ExoMars itself is kind of in limbo right now. So seismology has been tried many times at Mars, never successfully, but we're trying it one more time with GEMS, so the mission that I'm working on right now, it's a JPL managed mission, the Lockheed Martin spacecraft. We use the Phoenix heritage, both in terms of hardware and the roles and relationships, to the maximum extent possible to control cost and risk. Landing on Mars is actually very expensive, and the discovery cap has been thought to be too low to support a Mars lander mission. And we've been able to get around that by a couple of things. One is using previous spacecraft, and we use it just about as a carbon copy as close as possible, and by getting all our payload from foreign contributors, which is at no cost to NASA. So by using those 2 tricks, we've been able to get it just down below the discovery cap. It's a strongly international mission. Like I said, both these instruments are foreign contributions, but it's not just as a cost trick. These are actually the best instruments, the best technology available. And so we've gone out and gotten the best technology, the best talent from wherever we can find it in the world and brought it together to do this mission. So in terms of schedule, we've got a launch in 2016. A 6.5-month cruise to Mars. That's as fast as you can possibly get to Mars, and that's because we're sitting on top of an Atlas V launcher. It's the same thing that launched Juno, and that thing could probably throw us at Pluto if we wanted to, because it's a really small spacecraft. But the Air Force doesn't subsidize little planetary launchers anymore, so you either got the big one or you got nothing. So we get to Mars in about half a year. We go directly to the surface, direct entry, no orbiting when we get there. Once we get to the surface, we commission it for a month. We deploy the instruments, get the spacecraft all squared away, and then we spend a Mars year just sitting there quietly listening. So Here's the spacecraft. It's, like I said, it's a Phoenix spacecraft. It's closest humanly possible. The pie chart there in the bottom left-hand corner shows you sort of the degree of heritage. 77% is just a pure Phoenix rebuild. We're not using existing parts like Phoenix did from the 01 mission, but we have all the blueprints, all the specs, and so we're just going to stamp out another copy for 77% of it. We have minor modifications to about 20% of it, and only 3% of it is really major modifications. And so this should be a very, very safe and very low-cost spacecraft. In terms of mission design, here it is. It's a Type 1A orbit in the orbital dynamics parlance. We've got a launch period of about 20 days in 2016. And there's a whole bunch of specs here. If you come from JPL, you got to put one of these things up. Every mission I've ever seen has one of these, and they're kind of cool, but there's not a lot of new information there, I guess. So Phoenix cruises to Mars, all buttoned up in the capsule. If you saw the animation last night, you get some idea of how exciting this whole process is. It ejects those wings, the solar panel wings, just before it gets to Mars, and then it enters the atmosphere on a heat shield. Scrubs off a lot of that energy until it can deploy its chute. Once the parachute's deployed, it descends through the atmosphere, it ejects the heat shield, puts down the legs until it's about a couple of kilometers above the surface, in which case it cuts loose from the parachute and then flies down to the surface on rockets, much the way Viking did. And once on the ground, it deploys the solar arrays, the antenna, and the robotic arm, which in our case is not for digging in the ground like for Phoenix, but is for picking these instruments up off the deck, putting them down on the ground so they can do the measurements the way God intended them. Okay, so here's that entry, descent, and landing thing on a single chart. This whole process goes from about 100 kilometers down to the ground in about 6 minutes. It's a pretty frightening experience if you've ever been on one of these missions or been close to one, because you're really depending on the spacecraft to do everything the way you designed it, and there's about 1,000 different things it has to do just exactly right to get to the bottom in one piece. So for our payload, we've got 2 instruments. We've got a seismometer and a heat flow probe, but we have 3 investigations because we also have a rotation and interior structure investigation that's based on the X-band transmitter. So we have 4 payload elements: size, the seismometer, HP cubed, which is the heat flow and physical properties probe. We have 2 support payload elements, the instrument deployment arm and a camera that sits on that arm, so we can actually map out this little bit of terrain that we need to put the seismometer down on. And then we have this spacecraft system, the telecom system, which we use to do the rotation measurements. And so here's the payload. A lot of this hardware actually already exists. The arm we're using was supposed to fly on the Mars 01 lander, which never was launched because of the Mars Polar Lander failure. So this is actually the flight arm, the one that was going to be bolted to the spacecraft to go to Mars. It's already checked out. All we have to do is bolt it on and use it. It's not that easy, but close. The camera is just a MER nav cam. It's the same as the cameras they're using for navigation, for mobility on MSL. And so JPL actually has dozens of these things sitting around for tests and things like that, so we'll be able to pick that up on the cheap. We've got the X-band transponder, which again is sort of standard deep space equipment. We've got a seismometer and the heat flow probe. And so a little bit about each one. The seismometer we're using is being built by the French. This has been developed over the last 20 years for these various missions and is as sensitive as the best research seismometers on the Earth right now. And so both in terms of its sensitivity, in terms of its spaceworthiness, this is a really high level of development. It's got 6 components, 6 different sensors in it. It senses in 3 directions with a long period sensor, which gives you vibrations from just a few hertz all the way down to periods of the Phobos tide, which is 8 hours. It could actually pick up the solar tide, except for the thermal noise will swamp it, but we'll be able to see the Phobos tide. We'll be able to see free oscillations of Mars. We'll be able to see surface waves. And then we have a short period seismometer, which is micro device. That's about the size of a $50 to get the high frequencies. It overlaps at a few hertz with the long period instrument and goes all the way up to about 100 hertz to get the high frequency seismic activity. The heat flow probe is being built by DLR in Germany with some help from the Austrians. It's a self-penetrating mold, the same descendant of the mold that flew on Beagle 2. It has a little hammer inside, and it just knocks itself down into the ground. It's going to go down to a depth of about 5 meters below the surface, and trails behind it a tether. And on this tether are thermal sensors every few centimeters, every 5 or 10 centimeters. And by trailing this tether down there, we'll be able to get the thermal profile of that upper 5 meters. And when you have a thermal gradient and you measure the thermal conductivity, which we'll do with this as well, you can get the amount of heat that's actually moving out through that layer of ground. And since the layer of ground is all the heat that's coming out of the planet, that gives us a strong constraint on the heat loss of the planet today. And finally, the RISE experiment using the X-band tracker, we do Doppler ranging to the lander. We do this in orbit to get the gravity, look at accelerations in the spacecraft with the gravity. If you're sitting on the ground, you're bolted to the planet, so then what you're actually doing is tracking the surface of the planet as it rotates around. And so by using this Doppler tracking, we can get the lander's location to a handful of centimeters on the surface. So I'll say that again. We can get the location of the spacecraft to that kind of accuracy at Mars distance. And this is something that they do routinely. We do that for the MER landers when they stand still long enough, but we need to be able to do that over several months, 6 months to a year of tracking in order to be able to start pulling out these very subtle variations in the Mars rotation vector. So Spirit was going to do this for us if it woke up after its sleep last winter. Unfortunately, it didn't wake up, and so this may be the first chance we get to do these kinds of measurements since Mars Pathfinder. And then we have the arm and the camera, which I've already talked about. Okay, so I'm not going to go into this too much, but it's just suffice it to say that normally when you do seismology, you do it from a network of stations. You have seismic stations that are distributed across the surface of the planet. You put together the signals from all these different seismic measurements. You get travel times from that. You get first arrivals, second arrivals, things like that. And you put together a travel time curve and get the interior structure. And so much of the effort in the last 15 or 20 years has been towards trying to get a seismic network mission to Mars. And of course, launching a half a dozen or a dozen spacecraft all at once is exponentially more difficult than getting one off. And so we've been able to sort of, cut this Gordian knot by invoking some sort of state-of-the-art seismic techniques that have been developed over the last 10 years or so to take single station records and do analysis on those records and be able to pull out the geophysical parameters that we're after. And so we have about a half a dozen of these kinds of techniques that we've identified that will allow us to get our science goals. In addition, even though we have several lines of analysis that indicate a relatively high level of seismicity for Mars, I mean, we can look at what we got on the Moon. We can look at the density of faulting on the surface. We can look at our theories for how fast Mars is cooling and contracting. As it contracts, it's going to crinkle and crackle. All those things indicate that we should see something of the order of 100 relatively large events over the lifetime of our mission. But even if we're wrong, we have some guaranteed seismic sources, sort of non-traditional signals. We know that there are meteorites impacting on Mars. We see them with HiRISE. We can get at least bounds on the frequency of those, and we can show that analytically we'll see probably somewhere between 40 and 200 impact events, which again create seismic waves that we can use. We can use the Phobos tide again to probe the deep interior. It's very effective, especially getting very deep structure. and the atmospheric interaction with the surface, which produces noise. It turns out that the hot topic in seismology these days is noise analysis. You can actually analyze the noise, and over a period of time, you can start pulling out things like the crustal thickness and seismic velocities and things like that. So we have some guaranteed sources of signals. So even if Mars is not cooperative, we should be able to get all our science goals again. Plus, we've got the precision tracking that is very complementary to the seismology and the thermal measurements to give us a handle on the thermal state of time. So here's our surface timeline. We land, and in the first 30 days, we have a lot of activity. We check out the spacecraft. We characterize the spacecraft itself and its vicinity. We start mapping out the work volume of the arm. We do a second sort of entry, descent, and landing for each of the instruments. So once we've gotten down to the surface of Mars, we're still about a meter away from pay dirt. So we have to make another sort of entry, descent, and landing procedure to get that last meter down. And then we check out the instruments on the surface. We send the mold down to its depth. And then about Sol 31, we basically turn off the switch of our transmitter on Earth and just listen for another 2 years, 1 Martian year on the surface. Through Martian summer, winter, dust storm season, we've got margin on the solar panels to accept the dust load, the whole business, and we should be able just to accumulate data for that whole year. So in terms of status, as I said, we're one of 3 missions that were selected in Step 1 out of about 28 proposals, so we consider ourselves very fortunate. We're up against a Titan Mare explorer. It's called Time. It's actually something that lands in a methane lake on Titan, floats around and does a bunch of measurements. And Chopper, which is a comet hopper, it lands on a comet, goes off the comet, lands again, and follows this comet through periapsis. And so those are both very intriguing, very important missions as well. So we'll be fortunate to win against them, but we're certainly going to do our best, and I think we've got the best mission of the bunch. And sometime next summer, NASA will choose one of these missions to continue, and hopefully it'll be GEMS. So thanks.
Okay, my 2 questions are, will the GEMS mission give us any insight on why or how the pole tip of Mars has been so large? Some of the talks have said it's been up to 50 degrees, part of the history, and why or how often that changes. And also, it doesn't sound like it, but do you have to run the mission on Mars time?
Okay, so the first question is yes, and the reason is because that obliquity change is just classical dynamics. If you have a sphere that's distorted, it's not perfectly round, it has a density distribution, and start spinning it, it's just like a top. And you know how a top starts wobbling around, and that's just determined by the speed of its rotation and its internal structure. So the better we can understand that internal structure, the better we'll be able to actually plot back in time the history of that rotation vector. The second question, we will probably be on Mars time for those first 30 sols because we'll need to pull every bit of performance out of things to get everything done those first 30 sols with margin. But like I said, after we finish that initial stage where we're putting things down and checking things out, we're just going to go into sort of an automatic mode. We will have regular contact with the spacecraft, mostly for just housekeeping and engineering purposes. But that'll be on a 9 to 5 kind of a schedule after that.
Thank you.
Hi, Rick Smith. Obviously, you would like to have more seismographs, but let's say that somehow you were able to triplicate your mission and put them down on different parts of the planet. How much would that help you?
It would help a lot because, like I said, the standard seismic analysis takes basically seismic arrivals at multiple stations, and then uses that to triangulate back to the epicenter, and then you can plot out the path, and then you know where your seismic wave's gone, and that's all done fairly easily. It's done with the easiest thing to pick off of a seismogram, which is the first arrival, the P wave arrival. All the analysis techniques I'm talking about really depend on waveform analysis, and so you have to have a clean record. You have to have relatively large events, and and so it's a little bit riskier in a sense that you can't live with as much noise and as much uncertainty. And so if you had multiple stations, you'd be able to use all these sort of classical seismic techniques to get that information. And so we'd be able to still use the techniques we're talking about, but that would add a lot of strength to the analysis. And also, it would just give you a bigger distribution so that you can use seismic events from many different places. We don't know a priori where what's going to be the seismic hotspots on Mars. We think we have some good ideas just based on the topography, based on the tectonic structures and things like that, but Mars could throw us a curveball there.
A pair of questions. One, the proposed payload does not include magnetometry for the induced magnetic field and the like, and I was wondering why. And the other question is landing region selection. Of course, I assume low altitude, but what are the latitudinal constraints, and what sort of terrain do you want to go down to? Northern plains, or rather smooth, low elevation highlands, or what? Because that's important for the heat flow.
Right. Okay, so the first question, when I first started putting together this proposal, we had magnetometers. We actually had electric field probes. We had long things that shot, long antennas that shot out about 20 meters in 3 different directions. We had a MET station with an acoustic anemometer on a big boom. It was a great mission, and it came in about $150 million over the cost cap. And so at that point, we had to either sort of give up on the mission or start ripping pieces off the payload. I can show you my scars if you like, because I had to kick off some of my best friends with these great instruments. And so every space mission is a compromise, and this is a compromise we had to make in order to fit within the cost cap. Discovery is very, very serious about cost caps. The Dawn mission, the PI of the Dawn mission is his field is magnetometry. NASA forced him to rip that magnetometer off the Dawn mission in order to stay within the cost cap. I think they did it just to make him squirm. But so they're very serious about it, and that's what we had to do. So we've tried to turn that into a feature. That we're focused. There's not a lot of things to go wrong. There's not a lot of complexity, and so that's where we stand in terms of that's why we don't have a magnetometer on there, which I'm still trying to figure out if there's some way we can sneak one on somehow. As far as landing sites concerned, that's the subject of a lot of analysis is going on right now. In our proposal, we did a sort of a quick and dirty analysis, and we got latitude constraints that were about 1 north to 15 south. And of course, since you're constrained to land at low altitudes below about minus 2.5 kilometers or so, there's not much in the south that you can go to because the south's all high. So it's a pretty narrow strip right around the equator. And we identified 2 or 3 different regions, one in Isidis, one in Acidalia, one south of Elysium that had nice, flat, featureless areas, which is actually good for us. The geologists hate this stuff, but featureless is good for us. So based on the solar insolation and based on altitude, that's kind of where our landing area is.
I actually had 3 questions, but would it be practical to put seismometers on the landing legs of all future spacecraft, below the shock absorbers?
My answer to that would be yes. You ask a flight system engineer, and he'll run screaming from the room. But we've actually proposed seismometers for every mission that's gone to Mars, and it's really tough to get something on the payload that's not part of the core mission of that spacecraft, because again, every spacecraft that goes out there is constrained in a box from every different direction, and they're getting pushed on mass, they're getting pushed on power, they're getting pushed on money, and if you're sort of an afterthought, you just don't get very far. But I think, in principle, yes, that would be something that I would advocate.